Let's look at a fictitious scenario. So imagine a scenario where the smoke from a local industrial refinery fire carried toxic chemicals downwind, eastward, into the surrounding environment. It is your task to find out, number one, did the toxic chemicals stay in the dirt or water, or did it get metabolized into the ecosystem? Two, what are the concentration ratios of the toxic chemicals in the soil or water versus plants, insects, and animals? Three, does the toxic chemical negatively impact mature plants, insects, and animals? Four, does the toxic chemical negatively impact the development of plants, insects, animals into maturity? And five, does the toxic chemical inflict DNA damage that is passed down to offspring? So as an insect biologist, you're tasked with answering these questions. You choose a species of beetle that is both prolific and central to the local ecosystem. Every beetle needs to be measured to observe a pattern of differences versus toxin amount. So for each beetle, there's properties that you're going to measure. You're going to measure the weight, the length, and maybe the length of the head, thorax, abdomen, legs, feet, wings, and antennae, the coloration, the gender, the age, the concentration of toxin in the beetle, either maybe in its chitin or internal organs, and its DNA, and more variables than that. So here's a spreadsheet of some of the data of some of the properties you need for each beetle you study. So we need a beetle ID, so some kind of unique identifier, the weight of each beetle, the gender of each beetle, the age of each beetle, the amount of toxin that was found in each beetle, maybe the color of the thorax, color of the wing, and various other properties that we want to measure. So you have a limited amount of time and a limited amount of money to collect, measure, and analyze the data and equipment and consumables. And you have a deadline of 6 months to submit your complete definitive report. It should not take you long to realize you have many problems. So there's a number of issues here. So the first one, issue A, is the population of beetles that live east of the refinery may be literally in the thousands. So measuring all of the beetles in a population is a monumental task. This graphic below is only 600. So imagine yourself slowly, carefully, diligently, accurately measuring each of these beetles, let alone thousands. So the problem is measuring all beetles in the population would take more money and time and sanity than you have. The answer, statistics provides an answer. So do not measure the entire population. Instead, trap a small number of beetles, that's your sample, which represents the larger population. Statistics allows you to calculate how many beetles you need to measure to know if the differences you see are significant or not significant. So the solution is perhaps to have a sample size of only 30. And so measuring 30 beetles is a lot better than measuring thousands. So a sample of 30 is both cost and time manageable versus a larger population is not cost and time manageable. Next, if you measure beetles under the smoke cloud, the problem then how do you know if the measurements are correlated to the toxin? The statistics provides an answer. You should take a sample of beetles from the affected area to the east and take a sample of beetles from the unaffected area, that's your control, to the west, in order to compare the weight of beetles that have toxin versus the weight of the beetles in the control area, the gender of the beetles underneath the toxin, and the gender of the beetles in the unaffected area. Ideally, you should make an effort to collect a simple random sample of beetles from both affected and unaffected areas. So here is a graphic where the red beetles are randomly selected sample beetles. I can't fit all of this on the screen, but literally this is 900 beetles, so this represents our population. And you can see that 30 beetles have been randomly selected from within this population of 900. So this shows an example of what we mean when we talk about a sample, which is representative of a larger population. Third, for the beetles that you do measure, what do you do with the numerical data and the categorical data? So the problem is, how do you see patterns in this data for each parameter? Another word for the parameter is going to be variable that you measure. So seeing patterns in columns of data is impossible, or at very best difficult. Statistics provides an answer. So you can take this data and make something visual. So you can create pie charts, bar charts, time series, and scatter plots, to name a few. Once you create these visuals, you will be able to see patterns in the data. So you know from past experiences that you can find the average of a list of numbers to describe and summarize the behavior of data. So for example, if you have a car or you drive a car or you're familiar with cars in general, cars have an average miles per gallon rating. If you go to the grocery store and you buy groceries, there's an average cost of groceries per week. So finding the average or the mean of the data is just one example of what is called descriptive statistics. Some others to be learned are standard deviation, median, and mode. And then lastly, real life is messy. There may be unforeseen factors which could affect your measurements and your results. You may follow every aspect of scientific methodology perfectly, but nature is simply unpredictable in the short term. So the problem is, how do you detect confounding variables? How do you account for randomness? Statistics provides an answer. Scientific knowledge is not 100% for at least two reasons. Number one, science recognizes there might still exist something outside current knowledge. Two, science operates on observation, doubt, skepticism, and testing. Continuous testing of scientific principles and ideas perpetually increases the accuracy and reliability of predictions. And knowledge does not need to be 100% to be actionable. Probabilities of less than 100%, like 99, 95, or even 90%, are typically good enough to make everyday decisions. So take, for example, apple pie is my favorite. I have not tried an apple pie from this bakery, but it is my best chance, highest probability to get something I will like. So having a high enough probability, which is still less than 100% of success, is good enough to make a decision. Or brake pads manufactured with a 95% confidence level are good enough for reliable and safe operation. The probability of all 4 sets of brake pads failing is 0.000000625%. So having a low enough probability of failure is good enough to be safe. Coupling descriptive statistics with probabilities of a rare event in a systematic method toward sample data allows a student or a researcher to infer conclusions based on evidence. This is called inferential statistics.